In this lesson, we're going to be looking at the input mapping layer. So what the input mapping layer is the first place that we are taking our PLC tags and putting them into our asset data blocks. So just as a quick refresher, if we have a look in our project tree and look at data blocks, we can see that we have global asset data blocks. And in here we have analog devices and all of our analog devices, and we have our valves. And what we're looking to do is to get the information from our hardware layer and put these signals into the relative asset data blocks. That's the first step of getting our asset orientated approach sort of nailed down in terms of raw signals. So if we look at our main OB, here we make a call to a function block, which I've called input mapping layer. And inside here, it's in SCL. It doesn't have to be in SCL, but that is the way that I like to do it. So in here, we have a region for map valves, and we have a region for map instruments. And what we'll find is for each type of asset, there is a type of mapping block. So if I hover over this map AVO1 here, we can see that this one is a function, and in the function, is a function block. And in the function block, we're expecting to have these inputs here. So IO open feedback, IO close feedback, alarm failed to open, alarm failed to close, alarm both limits active, and then the asset data itself. So if we have a look at map quarter turn valve, if I open this, so I've gone online and I will set my call environment to have a look at AVO1. So currently we're looking at the mapping layer for AVO1, and our IO open feedback signal, as long as that comes in on its own, we're not allowed to have the close feedback as well. Then we set our asset data IO input open feedback. We've set that to mirror this signal here. We do the same for the close feedback. And then what we do is we move our alarm indexes into the asset data alarms. And this will make more sense when we come on to managing the alarms later as to what this means. But essentially, we're setting the index number to look up the alarm in our array of alarms. And realistically, that is all that this block is doing. It's created to ensure that every single asset is managed the same way. So if we have a look back out on the mapping layer, we can see that map AVO1, AVO2, AVO3, they're all done the same way. AVO2 is a modulating valve, so it's slightly different. This is what I was getting at with the each asset has its own map type. So if we were to open this one and have a look at how this one's set up, it'll have the same thing to do with the alarms down here. And all this one is doing is saying IO feedback, move that into data.io.input feedback. So if we were to go and have a look at this value, data type here, this allows us to have a look at everything that is in this asset data. We're currently at this layer here, which is IO, and we're looking at input feedback. This is where the information from our hardware layer will end up through this mapping layer, but in the corresponding asset. So if we look at MVO2, modulating valve 2, I know I've called it AVO2 in the comments, but MVO2 here, we look at typed IO input feedback. That's where our value is going to end up on this this variable here. And if I just go back to here, we've got the same for map AVO3, AVO4, AVO5, MVO6, just using their corresponding asset mapping variables. Now, one of the reasons for doing this is because you reduce the amount of opportunity there is for errors. So by going through a dedicated mapping layer, what we're doing is ensuring that a standard valve or quarter turn valve can only be mapped to a quarter turn valve. For example, if I change this to MV02, which is a valid block, and you could accidentally type that in, you can't actually put any information in there because TIA Portal's aware that it's not the correct data type. If you hover over that for the error, it'll say that it's not transferable to the correct parameters. So parameters of the function or function block do not match the transferred formal parameters. So really rubbish way of saying they don't match. So that has to be AV03. You could end up putting AV01 on there, for example, if you do a copy and paste error, and there's nothing stopping that because the data types do match. But it's better than having all of your asset data loose and doing move commands or equals in SCL assignments and things like that, especially if your asset data has an awful lot of signals coming in from your hardware layer. If this was a complete system, for example, just say all these valves made up a complete system and you were moving everything required for that system in one go as one big asset, not having double the amount of inputs, because you'd have to assign the inputs on both sides, the hardware side and the software side, or just using them directly in the software. This approach is easier and better in terms of reducing the amount of errors that you can have, and also knowing that if you ever do have something that is a input sort of error or something you suspect is coming from the hardware layer, this is the best place to come and have a look for it. Whether you've missed something or whether you need to modify something, here's the best place to do it. That brings me on to one of the other reasons why it's good to segregate your input mapping from your project, and that's sort of down to containerization. Everything in our project that's sat between input mapping and output mapping is containerized. We can go and change things on the input, such as, for example, if on our next project, instead of the signals for the AV01 valve coming from hardware, coming from our physical PLC hardware, it was passed over Modbus, for example, via a client. Well, all we need to do is change this part here, where the signal is coming from. We can go off and create a Modbus block that interacts with the server or the client or however we're getting that information, and plug it in here, and know that no code in the rest of our project needs to change, because all we're doing is modifying the raw data that comes into our project. The other thing as well is if, for example, we needed to do a one-off special thing to a particular input, for example, this one needed to be multiplied by 1,000, which I don't think it's going to let me do. But sorry, this is a Boolean, isn't it? It wouldn't let me do that. If we needed to invert this one, for example, we can do that without modifying any core code in our project. So if you have standard project code in terms of you create the same machine or the same process every time, it's much more likely that your input mapping layer or where signals are coming from or how you interface with other people's machines, if that sort of stuff is changing more frequently than your project, then segregating stuff out like this means that you can standardize your main project in the middle, but have free reign to change how you obtain information to put into that project. And that way of thinking starts really coming into its own when we start putting standards around our assets, because being able to freely change how you obtain signals and how you obtain information to pass to your assets and controls without having to change your assets and controls really comes into a strength for putting stuff into a library and making it reusable. So that's the valves, but realistically the instruments are pretty much exactly the same. The difference with instrumentation is that you'll notice here we have simulation data. So we do also need to simulate valves and things like that, but we'll come on to that in the next lesson where we're upgrading things to work for simulation purposes. But right now, let's just have a look at how the simulation works. So we have here a map level. Let's go in and have a look at, sorry, not a map level, a map analog signal. So map and analog asset here. Let's open this and have a look at how it's working inside. So inside a analog asset mapping block, it works the same way as the valves did or devices do. We have the same core principles of we're moving analog signals into our asset data IO input raw. So we have the raw value in milliamps or in volts or whatever it is coming into our hardware. That gets moved into the raw place, the raw value in our asset data block. But we also have this simulation active. And if that's turned on, which it is right now, we then update the same assets, the same variable in the same asset block. It gets updated with our simulation value, which allows us to act as if everything is wired up, is connected and is working. And our main project does not know the difference, basically. It doesn't understand. There's no link between the input mapping layer being in simulation mode and our project. So you can guarantee that anything you pass in its raw format will be acted upon by your project in exactly the same way as it would with a real instrument attached. Then we have the mapping alarm indexes, and that makes up the rest of the block. So it's very straightforward. There really isn't much to it. You can elaborate with this and you can expand on this. So you might say, for example, you want to introduce some randomization of the signal when it's in simulation mode, and sort of make some noise on it, or have some ramping occurring, or a feedback system that comes back. So when you make changes to a valve position in your code, it has a delay time until the valve actually reaches that position. All those options open up once you have the simulation layer intact and working. And we'll see more about the simulation as we go through. There is more to it because we build in a HMI simulation HMI to interact with this stuff. So it's not like you're having to come in here and mess about with this. And when we come to the HMI simulation section, we will go through this in a lot more detail as to how to build the correct data blocks, the UDTs required for simulation, and then interface all of that with a HMI to provide a platform in which to do your simulation. But for now, in the next lesson, we will look at providing feedback and simulation principles for a device. So we can have a look at what happens when we're in simulation mode for a device and how we use its own internal data to drive simulation.